say we want to do something that's like x squared. How can we do that? We can use Cmath library. And more specifically, I find where that went. Okay, cool. We can use Cmath. We can use somewhere in here. Pow. And pow will raise things to a power. It returns the base raised to the power exponent, aka the base to the exponent. So we need to, since we want to use something from the Cmath library, we need to include Cmath. We don't need to do any linking because we've already linked the std namespace using namespace std. And then we can come down here and we can do, we'll say double. I don't ever use float. You can if you want, but doubles just always work. So use doubles. Double. We'll call this result1 equals pow of some number x squared. And let's unravel this thing a little bit. So we want to get a power, so we're calling this thing that's a predefined function. And a predefined function is nothing more than it's a function provided by the programming language to ease computations. So they're going to be things like pow, like we're looking at, and say we want to raise 2 to the power of 2, so like 2 squared. This would be the syntax for that, which this is the function, pow, and these are your parameters, 2, 2. So I'm saying I want to functions we aren't going to talk about yet. They're a bit ahead of our time. Well, not ahead of our time, but ahead of our knowledge. But, well, writing them is, but using them is not. So this is a bit of a bad example since we're using the same numbers, but let's use, say, 2 to the 3. So I want to take this number, raise it to the 3rd power, and then this pow thing is going to return back what that number is. So 8. Because 2 times 2 times 2 is 4 times 2, which is 8. And that's all the predefined function is. You also have things like square root, which would take in a number like 25, and that would give you 5. That's the same as saying the square root of 25. And then there's also output manipulators that can format your output with cout, but we're not going to talk about those today. We'll talk about those tomorrow or Thursday. So let's look at that right now. So say we want to raise int x to the power of 2. Let's change this out to power. We can save our program. Oh, we should probably output that. Result 1 equals result 1. End line. We can then compile our program, run it, and we see the result is 4. Because we get this number 2, we raise it to the power of 2, and then we put that computation into result. We could see that with 3. Which would be 8. We could do, I don't know, 25 to the third, which is going to be a number I don't know, but the computer definitely does. That big number. Here, let's do this to even further our outputting abilities. We could say x raised to the power of power equals result 1. Compile that, output that, and we get 25 raised to the power of 3 is this crazy number. And then say we change that back to our 2 to the power of 3, it will easily do that. And then this is a good place to show us what happens if we edit a const. So say we do that, and down here, we want to say like x equals 4. If we try and compile that, we get a compiler error, which says cannot assign the variable x with const qualified, because we're trying to assign this value to a constant, and it will show you, note, variable x declared const here on this line, and you can go see, and then resolve that error, which here would be, I need to take that out, or not have that be a constant. So there's an example of power. Let's go over square root. So the square root of 25 of a number. We'll call this raising a number to a power. And this is a good way to show comments to you guys, because you see before I had x squared. Obviously, I'm doing x squared here. But when you guys come here, it's much easier for you guys just see, oh, this is an example of raising a number to a power. So let's say example of raising a number to a power. Example of the square root of a number. So let's do int base equals, here, let's just do this. This will be even better, because I want to teach you guys to be good programmers. Let's do this. And then we can do base equals 25. Double result 2 equals square root of base. So we're going to override this 2 we have here on this line with 25. And then we're going to take the square root of that number. And then we can come down and see out the square root of base is result 2. End line. And then we can save that, we can compile it, and we can compile it again, and then we can run our program, and we see the square root of 25 is 5. And say we don't want this to keep outputting because we're not on that example, we can just do that, comment it out, we can compile our program, run it again, and we'll only get the computation that's relevant to us. We can comment that out so that doesn't keep spinning. Let's talk about an example of the absolute value of a number. So we could say base equals negative this number. Double result 3 equals the absolute value of base. And this will give us the absolute value of base is result 3. Need to put an end line, so our output, our next terminal line will be on its own line. Save that, compile, and run, and we can see the absolute value of this negative number is the same number but positive. There's also floating point. Absolute value of floating point. Absolute value of a number. And we could do double float base. And then at this point, it's a good thing to do, since we're using different data types, to go back to all of these bases, and we'll put I underscore. So we know this is our integer base, this is our floating point base. Equals negative some numbers dot some numbers. We could do double result 4 equals floating point absolute value of floating point base. We can output that, the floating point absolute value of floating base is result 4. Save that. We compile it. Ooh, we forgot. Good little syntax error. See, no one's perfect in this world. I'll forget lots of semicolons, because lots of the languages I use, you don't have to use semicolons. Like Python and JavaScript don't have to have them. It's smart enough to know where to end the lines. Not saying that's the best. I kind of like the semicolons, but I'll forget them because I'm bad, I guess you could say. So let's add that semicolon in, save it, compile it. And how do I know it's a semicolon? Well, I go to the first error it outputted, which there's only one, so it's easy to find that. And it tells me right here, expected semicolon at the declaration on line 46 in example C++. So I go to line 46, and I saw there wasn't a semicolon there. So now it will compile. We can run it, and you see it gives us the floating point. That's weird. Really weird. Why did it do that? Didn't do that. Well, we don't have time to go back and examine all of that, but there's a reason why it did that, and I'll figure it out and get back to you guys on that next time. And then we've got, those are all the ones that you're going to need for your assignment, actually. So here's some other ones that you'll need throughout the semester. You'll need them in your lab, and you'll need them in your life. And they'll just help you out. So example of seal, that would be base equals, well, floating point base equals 12.2. Then see out the seal of floating point base is going to be the seal of what is it? Floating base is, oopsies, is, typing is difficult, that. And then we can compile that, which I forgot another semicolon. We can save that. We can compile that. We can run that, and we see the seal is that. Let's do an example of floor. Whoopsies. So seal is going to round up. As you see, 12.2 rounded up to 13. Floor is going to round down. So we can compile that and run it. You see it will round down. And then we can do, oopsies. We can do of round. So we'll do 12.2, and then we'll do 12.3 or 12.5. Run that, and you see the round of 12.2 is 12, and the round of 12.5 is 13. Say we want to use sine, cosine, and tangent. That's probably how you spell them. So we're going to need, those are when you're trying to find, what is it, the hypotenuse or something. I'm not perfect at the math behind it. I just know how to code it. But you need to input radians into sine, cosine, and tangent. And radians are they're another form of degrees. We always start with degrees in our computer, unless like someone's like really smart, they may like know how to input the radians, or like a program before us may convert them to radians, but for us, we need to convert them to radians ourselves. So we'll be starting at degrees if we ever use that. Sine, cosine, and tangent. So this is how we convert them to radians. We need to multiply the degrees by pi and then divide that by 180. But we haven't defined this pi yet. So we could come here and say something like, I don't know, double pi equals, and then I have a nice number for pi right here. So let's just slap that in there. And that's all good and dandy, but like, what if someone accidentally came down here and said pi equals 1? That's completely false. So how we want to do that to not make that be able to happen, we're going to take that out of here. And this is the only time you're going to be putting anything up here that's a variable, is when we make global constants. So then we can use it here. And then we can just simply do something like double sine result equals sine of radians. And if we output that, let's actually do this. We can save this, which, whoopsies, permission denied. Save as on the desktop. We'll call this test.cpp. Let me go find that on this side so you guys can see that. And then, so now we have that. We need to open a terminal window, which will start us at our home directory. So we're going to need to change our directory to desktop. And now that is our desktop right here. So we can just g++ test.cpp since that is on our desktop. And that will compile our program with the GCC compiler. And it won't work because nobody's perfect. What did we do wrong? Use of undeclared identifier. Did you mean degrees? See, so I'm not good at spelling at all, so I spelled digress here. But look, this is great because you guys can see this type of error. It tells us right here, error, use of undeclared identifier degrees. Did you mean digress? Did you mean degrees? And then it will show you right where you actually defined that and initialized, in this case, that global constant in this case. Wait, no, that's not a global constant. That variable in this case. So we can come back over here and we see that in test.cpp on line 13. So if we go to line 13, hey, we spelled digress. So there's degrees, save it, compile it. Whoopsies. That's going to mess us up since I just did that. Oof. Oof. There we go. We can compile that and clear all this crap, and then we can run it. And we get sign result is 0.5. And we can even go further and see out, let's say, what is it called? Let's put a new line of it. See out degrees is equal to radians. Don't forget the semicolon. Oopsies. And then we'll compile it with the G++, run it, and we can see that 30, the result of this calculation right here. Where is it at? This calculation right here. Let's space this out a little bit better. The result of this calculation right here is this number, 0.523599, which is the radian equivalent in degrees. And then we feed this number that we are storing in radians into sine, and it equates to 0.5, which we can output to the screen. Similarly, we can do something like this for cosine. We're just going to use the same radians amount, and we don't need to keep outputting that. But let's say cosine result. And then we can compile that and run that, and we see that from cosine we get 0.866025. And similarly, we can get tangent, which, let's change these all around. And we can compile and run, and we get the tangent answer. And that's how we use sine, cosine, and tangent from the C++ Cmath library.